So far we have shown 3 advanced solar cell concepts based on the design considerations we discussed in this course. We have discussed the passivated emitter concepts PERC, PERL and PERT. In this video we will show 2 solar cell technologies that focus on surface passivations in a different way. These technologies are the tunnel oxide passivator contact or TOPCon and the silicon heterojunction technology or HIT. This is a cross-section of the tunnel oxide passivator contact solar cell, abbreviated to TOPCon. We can see that front surface processing is more or less similar to the PERC solar cell family, but where the previously introduced localized contacts with a back surface field to reduce recombination at the back contact, in the TOPCon solar cell we see a different solution. In order to prevent the minority carriers recombining at the back contact, a very thin oxide layer of approximately 2 nanometer thick is placed in between the N-type base and the phosphorus doped N+ layer. As we have discussed in the previous video, N-type wafers have a favorable electrical properties over P-type wafers and are therefore gaining a higher fraction of the market over the historically favored P-type wafer base. In general, the minority carrier diffusion length in N-type wafers is larger than in P-type wafers since it has fewer metallic impurities. Secondly, N-type wafers are not sensitive to light-induced degradation, and important for application in TOPCon solar cells, thermal oxide passivation is easier realized on an N-type substrate. Since the oxide layer is present, it is almost impossible for the minority carriers, which are holes in the N-type wafer base, to reach the back contact of the cell, as they cannot pass the potential barrier introduced by the oxide layer. On the other hand, since this layer is kept very thin, electrons are able to tunnel through the barrier and be collected at the back contact with virtually zero loss. Contact patterning, which is a relatively difficult and therefore expensive processing step, is thus not necessary, and the backside of the wafer can be entirely metallized. An efficiency of up to 25.7% has been reported by ISE Fraunhofer Research Institute in 2017 with this concept, and it is still developed further. This is the world record efficiency for a monocrystalline silicon solar cell with both sides contacted. Both the PERC solar cell family and the TOPCon solar cells have improved the conversion efficiency of the cell itself by implementing optimal design features. The silicon heterojunction solar cell is the second high efficiency concept in this video with both sides contacted. Similar to the PERC family concepts mentioned in the previous video, the front of the solar cell is textured with random pyramids. However, in this concept, the front surface is passivated with a stack of layers consisting of intrinsic hydrogenated amorphous silicon and on top of that, doped hydrogenated amorphous silicon. During the plasma deposition process of hydrogenated amorphous silicon, dangling bonds on the surface of the crystalline silicon wafer can be passivated very well. Panasonic named the structure the heterojunction with intrinsic thin layer or HIT, referring to the H of heterojunction, the I of intrinsic and the T of thin. Here we see the band diagram of the emitter side of a HIT cell. Note that this diagram is not scaled properly in the horizontal direction, so the width of the depletion regions are not to scale. However, this diagram shows the main point. The band gap of amorphous silicon is 1.7 electron volt, while crystalline silicon has a band gap of 1.12 electron volt, and the junction is therefore a heterojunction. The Pi stack at the front of the solar cell simultaneously acts as the emitter of the cell by creating a barrier for electrons, whereas the IN stack at the back forms a back surface field. The deposition of the high bandgap amorphous silicon provides effective passivation and thus low surface recombination velocity. In combination with the high band gap, the low surface recombination velocity of the cell will benefit by having the highest open circuit voltage of all high efficiency concept solar cells. Charge transport on both sides of the wafer towards the metal fingers is facilitated by a transparent conductive oxide or TCO layer, as the conductivity of the doped layers is too small for effective charge transport. The thickness of this TCO layer is chosen such that this layer also acts as an anti-reflection coating. This makes the solar cell a bifacial cell, meaning that light can enter from both the front side and the back side. Light absorption of such a bifacial design will be increased as it can collect light that has been reflected from the surface underneath the cell. To ensure a good lifetime of the charge carriers, this concept uses an N-type wafer base instead of P-type to increase the lifetime of holes, although high-performing HIT cells have been made on P-type wafers as well. As already mentioned, most of the cell's layers are deposited using plasma-enhanced chemical vapor deposition, which will be discussed in another video. The most important advantage of this deposition technique is that the layers can be processed at relatively low temperatures of around 200 degrees Celsius, much lower than the 800 degrees Celsius used for the diffusion processes to make doped regions in standard crystalline silicon solar cells. This is a major advantage when handling the wafers, which can be made thinner, and it makes the overall production cost of this cell lower. The highest efficiency reported by Panasonic for the HIT cell is 25.6%. Recalling that the theoretical limit for the energy conversion efficiency of a single junction crystalline silicon solar cell is 29.4%, it becomes clear that the PV researchers are getting closer to that limit. Before we move on to the record efficiency solar cell concept, we will first introduce another design feature for increasing the performance of a standard crystalline silicon solar cell in the next video. To conclude this video, we have seen that the TOPCon design can replace the back surface field and localized contacts with an ultra-thin tunneling layer and full metallization at the back, resulting in a record efficiency of 25.7% for a both sides contacted crystalline silicon solar cell. The silicon heterojunction solar cell optimizes the open circuit voltage as the amorphous silicon passivation layers form a heterojunction with the crystalline silicon wafer. This technology favors a low production cost at the same time by low temperature processing and easy handling.